Just to recap what we have done so far when we were discussing the fundamental types, we discussed the Boolean type, which is a type of an integer and it can store 0 or 1 for false or true to store logical values. We have done this, and then we discussed the enumeration type, which was essentially integer constants, and they can store any value and you can have some names over for them to use them. Then we discussed character type, and we only discussed this character type. We did not discuss this thing because this is not that often used, but we saw that characters inside are essentially integers, and we saw that characters are represented by ASCII codes, and in the previous lecture we also saw that how we can manipulate those numbers to represent different characters. We also saw that how we can use these same numbers to represent images or pixels, or the sound files are also composed of numbers. Essentially everything inside in a computer is a number. Now what we need to do is we need to discuss the actual integer types. I mean, characters internally are integers, and enumeration types essentially integers. Boolean type is also an integer. Now what we are talking about are actual whole numbers, such as 256 or 120 or -200, something like that. And we have several kinds of integers available to us. We have short, integer, long, and we have unsigned and unsigned short, unsigned integer, and unsigned long. What we mean by this is that if we declare such as integer a equals to 10, or if we just declare an integer without actually initializing it, that means this integer b or this integer a can, or this variable a or b can also include values of 0, positive whole numbers, or negative whole numbers. But if we use this unsigned identifier right next to it, if we use this unsigned, that means that variable can only store 0 and positive values only. So to discuss what those values are and what could be the ranges of these unsigned and signed integers, what we need to discuss is how the computer actually represents the positive numbers as well as the negative numbers internally. We have seen that how the computer represents simple numbers using binary numbers, and in the previous lectures we have essentially discussed the unsigned numbers. What we mean by that is that if we have a let's make a byte or something like that. Let's say we have 8 bits, 1 2 3 4 5 6 7 8, and we are using all of those 8 bits for magnitude only. Let's say we have let's pick a number. Let's say we have 1 0 1 1 0 1 0 1, and we are using just ignore this thing, and we are using all of these bits for magnitude only. So the actual number in decimal would be 1 2 4 8 16 32 and 64. So if we add 64 plus 32 plus 8 plus 4 plus 1, so what we get is 64 plus 32 is 96, 96 plus 8 is 104, and that would be 108, and that would be 109. So that would be 109 in decimal format. So we are using all of those numbers, all of those bits for magnitude only. So we can have like 1111 1111 for maximum magnitude, which could be had for an 8-bit number. So what we have is 1 2 4 8 16 32 64 128. So this number would be equal to, if you add all of these things together, so this thing would be equal to 256. Let me check it out. So 1 2 4 8 16 32 64 and 128. So if we add all of these things together, so let's go to a calculator. Where is the calculator? So we have 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. So we have 255, not 256. We have 255, the maximum possible amplitude which could be had if we had all of those bits on for an 8-bit number, or a 1 byte. Now we are talking about, and what's the minimum number we could have if we have all the bits 0. So that means this will be equal to 0 in base 10. So that means that if we are using all of those bits for magnitude only, then and we are only assuming that only positive value and zero values could be placed over here, that means that we can represent in an 8-bit unsigned 8-bit. If we have, I mean, it's just we are writing for ourselves, it's not a C++ identifier or anything. If we have an unsigned 8-bit number, the maximum range would be 255 and the minimum number would be from 0 if we are using only positive numbers. Now if we have let's say if we have a now we need to discuss that how are we going to represent the signed numbers. Signed numbers means that it would have a sign, some kind of identifier which can represent some kind of a sign next to it that either is positive or negative, or could be other things. Let's see how we can represent the signed numbers. Signed numbers means that positive values should be there with a positive sign, negative values should be there with a negative sign, and it can also contain zero numbers. So signed numbers are represented in two formats. One is known as sign magnitude format. In sign magnitude format, what we do is, if we have 8 bits like 1 2 3 4 5 6 7 8, if we have 8 bits, so we designate the most significant bit as a sign bit. Okay, so it's a sign bit and the rest of the bits are used for magnitude only. So let's say that if this sign bit is 0, convention is we take the number as positive. If the sign bit is 1, the convention is we take the number as negative. So let's say that if we have a let's pick a number. For example, we have only 1 2 3 4 5 6 7. We only have the 7 bits for the magnitude, and we have this bit for sign. So let's say if we put 0 over here, and that means we are talking about the positive number. And if we have, let's say we just go all the way to maximum 1 2 3 4 5 6 7. So the maximum number would be 1 2 4 8 16 32 64. So if you just add all of these things together, you will get plus 127. Now that's the maximum number in positive range we could have over there. Now if we place, and the minimum number would be, now we can go either way to a negative side as well. So we just draw this thing again, 1 2 3 4 5 6 7, and let's make it to the maximum value, 1 2 3 4 5 6 7. But instead of a positive number, now we are talking about the negative number. So we put the sign bit as 1. So what would be the maximum negative number would be? So that would be it will be, if this thing is only taken as sign bit and it does not have any magnitude associated with it, so we can have this thing as negative due to this, and minus 127. This sign magnitude format is useful for, this thing is 127, but since this thing is placed as 1, and so we took it as minus due to this. This sign magnitude format is useful when we are talking about analog to digital converters, in which we convert the analog values coming in from some sensor, or which is giving us some analog continuous time continuous valued voltage, and we need to convert it into digital numbers, because computer has finite memory and each memory is of finite size. So we need to convert it into discrete time, discrete valued, and you are going to see that in your signal systems and DSP course. But this thing is useful in analog to digital conversion, but this format is not that useful when we are talking about arithmetic, when we have to add two numbers, or we need to subtract two numbers, or we need to manipulate positive and negative numbers, because we need to have some extra code or extra circuitry associated with dealing with this sign magnitude format. An easier format to represent positive and negative numbers is 2's complement format. The easier format is to represent the sign numbers is known as 2's complement format. And what we mean by 2's complement, complement means you're inverting something. So let's say we have a number, let's pick a number such as number 5, and we are representing this number 5 in just 4 bits, because in 3 bits we can also represent in 3 bits actually. Let's start with 4 bits, and we have 1 2 3 4 bits, and the position of each bit, this one would represent 1, this thing would represent 2, this thing would represent, this bit would represent 4, and this bit would represent 8. So if I turn on this bit, the resultant number would be 8. If this turn on this bit as well, the resultant number would be 12. If I turn on this bit, the resultant number would be 14, and if I turn on this bit, the resultant number would be 15. So I cannot turn on 8 because the resultant number would be more than 5. I can turn on 4. The resultant number would now just include, I have turned on 4, that means I just need to turn on another 1, so that 4 plus 1 would be equal to 5. So that means that 0101 in binary format is equal to 5 in decimal format. Now what I need to do is I need to represent minus 5. So what we need to do is, I know that 5 is 0101 in binary format if you are talking about 4-bit only, because the rest of the bits would be 0, so no need to worry about that too much. So what I need to do is, first I will invert all bits. So if I invert all bits, what I get is 0101, or if you look into some code such as logic design, we invert means in C++, it means applying a NOT gate. NOT gate is, or NOT operator, which is represented by an exclamation mark. In your logic design you will be drawing this symbol, or if you have an integrated circuit you will be drawing a circle, and that's it. So that means whatever is going in or coming out or whatever is inverted. So if whatever is invert all piece means that this thing would become 1, this thing would become 0, this bit will become 1, and this thing will become 0. So whatever we have inverted all bits place by place. So if we had a 0, we put a 1, if we had a 1, we put a 0, and so on and so forth. Next, what we need to do is, we have this number, let me write it down again somewhere else. Now add 1. So I need to do add 1 and make sure it's a binary addition. So it has a very same rule which you did in your decimal addition. So if you had we had a number, let's pick a number 27 plus 49 in decimal. So what we did was 7 plus 9 is 16, so we put 6 over here, and we had a carry of 1 over here, and then 2 plus 3, and that is 2 plus 1 is 3, 3 plus 4 is 7, so we have 7 over here. So that means that here, if you are adding binary numbers, so in binary numbers, if you add 1 and 1, so that would be equal to 2, but in binary format that would be equal to, let's pick a number over something like this. If you are adding like 2 numbers, so 1 plus 1 is in binary, that would be 1 0, because if you count in binary 0 1 1 0 1 1, that's how it works. 0 1 2 3. That's you just need to, we're talking about decimal numbers over here, but 0 1 1 0 1 1, that's how we count, and then we had 1 0 0 and so on and so forth. We need to remember that. So let me write it down here again, that if you want to do 1 plus 1, that would be 0. 1 plus 1 is 2 is 1 0, so I put 0 over here and I put 1 over here, and 1 plus 1 is 0, and 1 plus 1 over here is 1 0. Okay, so you can just put 0 over here, and there is nothing over here, so this become 1 0 0. So that is actually equal to 1 0 1 is 1, and 1 1 is 3, so 1 plus 3 is 4, and that we got here in binary, the 4 over here. So if we just add this number, 1 plus 0 is 1, and we had 1 0 1, this number is equal to minus 5 in decimal. How we got minus 5 over here? Let's see. Let me write it down, this number. I'm saying that a little bit more. This number is minus 5. The first thing I need to see that this bit is 1. That means it's a negative number. In 2's complement we have a sign magnitude format. Actually it's also a sign magnitude format, but this bit, the most significant bit, this most significant bit has a sign and magnitude associated with it. Since it is representing a negative number, so that means we are talking about the negative number. So we have 4 places, 1 2 3 4, and this bit will represent 1, this bit will represent 2, this bit will represent 4, and normally this bit would represent 8, but since this thing has now associated a sign with it, so this thing would represent minus 8. Let's see how it works. So 1011, if I put 1011, so that means that minus 8 is active, 2 is active, and this 1 is active. That means minus 8 plus 2 is minus 6, minus 6 plus 1 is minus 5. And that's how the computers actually represent negative numbers, because here it is actually simplifying things, because we do not need to write another subroutine, or we do not need to make another circuit to add numbers or subtract numbers. What we can do is, let's say I need to subtract 10 minus 7, or just to make it simple, let's say I need to subtract 12 minus 7. That means that I can do this thing as 12 plus minus 7. So if I can take the 2's complement of 7, I will get minus 7, I will get a negative number, and I just add these things together, I will get 5 over here. I'm going to demonstrate that in a moment, how it's done. Or let's do it here, right here. Okay, so 12 is, I mean, the point is that using the addition using the circuit, or using a subroutine, or using a function which can add numbers, we can also subtract numbers just by taking the 2's complement. So what we need to do is, we need to do 12. 12 is, I mean, we are just doing 4 bits. You can just extrapolate it with 8 bits as well. 12 is in binary format. We have 4 bits. Let's write their placeholders, 1 2 4 8. So if I but I cannot represent, oh yes, I'm going to revisit this thing in a moment. I cannot represent 12 in this 4 bits because it's a positive number, and let's discuss the range here. Sorry about it, I'm going to do it later. Okay, so let's discuss the maximum range first, because this 12 needs actually 5 bits. I'm going to discuss why it's that. Okay, so if you have a 4-bit 2's complement representation, this bit is a sign magnitude bit. So that means if this thing is 1, this bit is 1, so we are talking negative number, and this bit is 0, we are talking positive number. Let's take the first case. Let's say, or the positive case, not the first case. Let's say that this bit is 0, and the maximum magnitude over here would be all ones. So that means 1 2 4, and the maximum range would be plus 7 in positive side, and in negative side we have if we put in this bit as 1, in this bit, if we put this sign bit as 1, sign magnitude bit as 1, this thing is actually representing minus 8 over here. This thing is representing minus 8 over here. What can we place over here? What can we place over here? Can we put all the ones over here, or can we put just zeros over there? Actually, if you take it intuitively, we can just put only zeros over here for the minimum value possible in this 4 bits. The reason is, if I want to convert this 7, if I want to convert this 7 to minus 7, what I need to do is, I take the 2's complement, and what I need to do is to 2's complement. I have the positive value of 7. I invert all bits, so I invert all bits, and I mean, just making a symbol of inverter, that's it. I mean, logical inverter, not the electrical inverter. Okay, so I will get 1 0 0 0. So that means that if I just, and then we add 1 to it, add 1, I will get 1 0 0 1, and this number is going to represent minus 7. The reason why I did that was if this bit represents 1 and this bit represents minus 8 plus 1 equals to minus 7, and we have a negative number over here. So in this, coming back to this question, so let's say we have a 4-bit number and we are saying that it's a negative number. So can I put all the ones over here, or can I put to find the minimum value? To answer this question, let's go back to the original example. I'm going to wrap up testing up again, and really simple. The minus 5 was 1011. Minus 5 was 1011. So that means I'm going to come back here again. Minus 5 equals to 1011. It was minus 8, 4, 2, sorry, 1, 2, and this was 4. 4 is off. Minus 8 plus 2 plus 1 equals to minus 5, and that's it. If I have this number, I need to convert it back, convert it to positive. We follow the same principle. First, invert all bits. I'm going to invert all bits, so I will get 0 1 0 0, and then I add 1, so I will get 0 1 0 1, and we see that 1 2 4 minus 8, we get 4 plus 1 equals to 5. So that means that if I have a negative number, I just take the 2's complement to convert it into positive number. If I have a positive number, I just take the 2's complement, which is inverting all the bits and adding 1, and I will get the negative number. So going from positive to negative and negative to positive follows the same process. Now let's say if I have 0, let's say if I have 0, how I'm going to represent 0, and that's why the reason why we actually use 1's complement is going to become clear over here. There is no such thing as negative 0. If I multiply a negative with this thing, I will get 0 over here. So I mean, plus 0 and minus 0 doesn't mean anything, but if I get negative, let's say somebody wants to do 12 minus 0, so I mean, he or she will get 12 over here, right? So let's say if I want to invert the sign of this thing, even though it's actually not possible to do so because that's kind of not that wise thing to do, but let's say if I apply 2's complement, what should I get? Invert all bits, 1 1 1 1, and then add 1. So I will get, let me write it here again, 1 1 1 1. I add 1 over here. So what I get is 1 plus 1 is, in binary 1 plus 1 is 2, but in binary we get 1 0, we get 0 over here, we get 1. 1 plus 1, 1 is carry over here. 1 plus 1 is 1 0, we get 0 over here, 1 is carry. 1 plus 1 is 1 0, we get 0 over here, 1 carry. 1 plus 1 is 0 over here, and we get 1 carry, but this thing is discarded because we only have 4 bits to do that. So I mean, if we had a 5th bit, it will be like I mean, that thing, I mean, we have just 4 bits over here, so we're just going to discard that. So that means that this number will still remain 0. Now coming back to let's do that. What if we had minus 1? So what is actually 1 is 0 0 0 1. So we invert all the bits, we get 1 1 1 0, and if we add 1 to it, so we get 1 1 1 1. So this thing is actually equal to minus 1. This thing in decimal and this thing is in binary. And why this thing is equal to minus 1? If you convert it into binary, 1 1 1 1, 1 2 4 minus 8, because the last bit is actually the sign bit as well as the magnitude bit. If we add these numbers together, we get minus 8 plus 4 plus 2 plus 1. 4 plus 2 is 5, 6, 7, and we get -1 over here. Coming back to the original problem. Was that what is the maximum number I can put over here, or what should be the bit values would be, so that I can get the minimum possible value. The minimum possible value, if I place, let me do it in some other color, so that I have two combinations right here. So we have 4 bits. If I place 1 over here, so I'm talking about -8 over here, so that thing is not that difficult to understand. If I put ones over here, if I add all these numbers, so I get equals to -1, but I want to get the minimum possible value. So if I obviously I need to remove these things, so if I this -8 bit, I activate this bit and I put zeros over here, I will get the value of -8, because all of these bits are now deactivated. That means the minimum possible value would happen whenever, and let me write those numbers for you, that if we have 4 bits, so maximum possible value would be maximum positive value on all ones. So this thing is equal to +7, and the minimum possible value would be 1, and this thing would be all zeros, and this thing would be equal to -8. I cannot put ones over here, because that in that case it will be a -1. And let's do the counting, and what I'm going to do is I'm going to make a table, or write a list for you, so that I'm going to write numbers. Let's say -8, -7, -6, -5, -4, -3, -2, -1, and then it have 0. And after that I have 1, 2, 3, 4, 5, 6, 7. So let's write the codes. Let's say I have just 4 bits, so this thing would be equal to 0, 0, 0, 0. This thing would be equal to 0, 0, 1. I'm talking positive numbers over here, so this sign bit is actually 0, 0, 0, 1, 0, and this thing would be 0, 0, 1, 1. This thing would be 0, 1, 0, 0, and this thing would be 0, 1, 0, 1. This thing would be 0, 1, 1, 0, and this thing would be equal to 0, 1, 1, 1. 1, 2, 4, just add them together, you get 7 over here. Now the next part is, what is -1? So if I take, and I'm going to write it in red mark, if I take the ones complement, invert all bits, what do I get? I get here, or let's take the, I think I've done it before. So if I invert all bits, I get 1, 1, 1, 1 and 0. Add 1, I should get 1, 1, 1, 1. So I will get 1, 1, 1, 1 over here. 2's complement of 2, I should get -2. I mean, this thing is equal to -1, right? So I just place it over here. And 2's complement would be invert all bits, so that would be 1, 1, 0, 1. Add 1, 2 here. So if I add 1 here, so that will be 0, 1, 1. So it will be 0, 1, 1, 1, 0. I will get 1, 1, 1, 0. So what about here? If I take 2's complement, so invert all bits, 1, 1, 0, 0. Add 1, so I get 1, 1, 0, 1. 1, 1, 0, 1. Let's hope I'm doing it okay. So yeah, probably okay. And what about 4? Just invert all bits, so I get 1, 0, 1, 1. Add 1, so if I add 1, I should get 0, and 1 is carry over here, 0, and 1 is carry, 1, 1. So I get equals to 1, 1, 0, 0. And last one, no, not last one, 5, which has this invert all bits, so I get here is 1, 0, 1, 0. Add 1, I would get 1, 0, 1, 1. Get 1, 0, 1, 1. 6 is just, I need to represent -6. So what I need to do is I invert all the bits, so I get 1, 0, 0, 1. Add 1, so 1, that would be 0, 1 carry, 1, 0, 1. So I get 1, 0, 1, 0. And the last one, -7, I should get, I mean the next number would be 1,000,000, but that would be a negative number. Okay, so here if I just keep on going here, so this thing would be invert all bits, 1, 0, 0. Add 1, I should get 1, 0, 0, 1. 1 0 0 1. And then the last number, I do not have plus 8 over here. I cannot represent plus 8 because I need to activate this bit, but this thing would be negative. So I just put, for minus 8, I put this, activate this bit, sorry, not minus, sorry. If I just put 1 and all 0, so this bit is representing a negative sign as well as the magnitude, and that's how we get the minus 8 over here. So if I just take 2's complement of this number, I will get plus 5. If I get 2's complement of this number, I will get plus 2. So if you need to get from positive to negative and negative to positive, you just take 2's complement and that's it. So not coming back to what is the maximum range that was possible if you had only 4 bits in sign magnitude format. In sign magnitude format, what's the maximum range which is possible in sign magnitude format? And we are talking 2's complement and 2's complement because that's pretty much the standard used everywhere, because reason is that you can use the same additional subroutine to add or subtract numbers. Oh yeah, we had an example which we saw later. Did I see later somewhere? Oh yes, over here. I cannot do 12 minus 7 because the maximum, first I need to discuss the maximum range if we had only 4 bits. So that means that if this bit is 0 and all of these bits are 1, I get plus 7. And this bit is 1, all the bits are 0, I get minus 8. So that means that if we only have 4 bits, the maximum possible range is the whole maximum range would be minus 8 to plus 7. Minus 8 to plus 7. We still have 16 numbers. If you just add them if you just count them, like how many possible combinations can you have? 0 0 0 0 all the way to like 1 1 1 1. We have 16 possible bit combinations. I think we have we have written all of these combinations over here, 16 possible combinations. If you just add, I've just written the table. You just 1 2 1 1 1 0 0 1 0 1 1 1 0 1 1 1, and then we start over here 1 0 0 1 0 0 1 1 0 1 0 1 0 1 1 and 1 1 0 0 1 1 0 1 and 1 1 0 and triple, all 4 ones. So we still have 16 possible combinations, but due to this thing, we are also counting this thing. So we have the maximum possible range going from minus 8 all the way to 0. We have 9 combinations. Going from minus 8 to 0, we have 9 combinations, and then we are left with just 7 more combinations. So we still have 16 possible combinations, but the maximum range goes from minus 8 to plus 7. That means that we can develop some kind of a formula that if we have 4 bits, the possible combinations for all of these, going from 0 0 0 0 to all the way to 1 1 1, not considering what these bit combinations actually represent, the maximum possible combination is 2 to the power 4. That would be 16 possible bit combinations. So that means that the maximum number would be if n is equals to number of bits, and equals to number of bits. That means that the negative number would be 2 to the power 4, that would be 16, and if I divide it by 2, okay, if I divide by 2, I get 8. So the maximum possible negative number, or the minimum possible negative number would be going from minus 8, and it will go all the way to 7. So I need to do is 2 to the power, I need to write over here 2 to the power 4 is equals to 16, and I divide by 2, I will get 8, and I should subtract minus 1, so I will get plus 7. That's the maximum possible positive number. So we can develop some kind of a simple formula. Let's say if we only had 4 bits, for 4 bits, if you are using 2's complement, the minimum number is minus 8, goes all the way to plus 7. So we can develop a formula like 2 to the power n divided by 2 all the way to 2 to the power n divided by 2 minus 1. I mean, the positive number would always be one less than, in magnitude form, one less than the minimum possible negative number. So minimum possible negative number here in this case is minus 8. So I mean, and the maximum possible positive number is plus 7. So whenever you are dealing with signed integers, the negative range would be one more than the maximum possible positive range. So I can just summarize this formula as if I just take 2 over here, I should get 2n minus 1 all the way to 2n minus 1 minus 1. So the maximum positive negative number, sorry, the minimum possible negative number would be from this to this. So let's say if we had an 8-bit number. In 8-bit number we have 8 bits. So if we are talking like unsigned number, so it will go from all zeros to all ones. That means the maximum possible combinations would be, in all bit patterns, would be 2 to the power 8. That would be 256. But since we are going from 0 to the maximum value, so this the range of this thing. The range of this thing would be 0 to 255. We still have 256 combinations over here, but we are also counting 0 obviously. So we have the maximum range would be 255. So we could write the range as 0 to 2 to the power n minus 1. 2 to the n is the number of bits, so 2 to the power 8 is 256 minus 1, so we have 255 over here. Now coming to, if we had an 8-bit signed number, if we had 8-bit signed integer, what's the possible range? 8-bit signed integer. So the minimum possible range would be all, I mean, if you have like 1 and all zeros. So we have 1, 2, 4, 8, 16, 32, 64 and minus 128. And the maximum possible positive number would be 0, 1, 1, 1, 1, 1, 1, 1. So we have 1, 2, 4, 8, 16, 32, 64. Add them together, you will get plus 127. So that means, because we are talking about the signed number, so we also have a negative number as well as a positive number. So the range is approximately broken in half for positive and negative, but the negative number would be one more than the positive number, because the last bit is actually used for sign as well as for the magnitude. So we have an advantage here in negative numbers, or some kind of a more range, slightly more range in negative numbers. So we can just write the formula as 2 to the power n minus 1 and all the way to 2 to the power n minus 1 minus 1. So we can have 2 to the power, I mean this is minus 1 actually represents 2 to the power n divided by 2, because we have the half range over here, and the positive number we cannot use this bit, so that we have one less than the negative number possible over here. Make sure you do not turn on these bits, because if you turn on these bits, then this number would equal minus 1. You can just do it as your homework. So 2 to the power n minus 1 would equal, if we have put 8 over here, 2 to the power 7 is 128 for negative number, and it will go all the way to plus 127. And let's pick a 16-bit number. If we have a 16-bit unsigned integer, we have 16 bits, so the minimum number would be 0 and the maximum number would be 2 to the power 16 minus 1. 65536 minus 1 equals to 65535. I just learned this thing. You can just do it in calculator if you want to. 2 to the power 16 equals to 65536, but that's the maximum number of possible combinations going from all zeros, to all ones. And you can see why this thing is actually quite difficult to write in binary. So what I'm going to write is 0 0 0 0 to all ones, and this thing is in hex. I mean, this thing is much simple, right? And if you want to write the binary numbers as hexadecimal numbers, this thing is actually much simple. So all f's means all ones. So I mean, since we have 65536 possible combinations going from all zeros to all ones, but we are also counting 0, so the maximum number would be from 0 to 65535. So let's say as the last example, or maybe the second last actually, if let's say we have a 16-bit signed integer, 16-bit signed integer, so that the range would be n is number of bits to the power n minus 1 to all the way to the power n minus 1 minus 1. So because I mean, just turn on the most significant bit, so you will get minus 2 to the power 16 minus 1 is 15 equals to 2 to the power 15 minus 1. So let's see what we have here in 2 to the power 15. 2 to the power 15 equals to 32768. So let's say we have minus 32768 all the way to 3. Sorry, should have drawn the errors for range. 32767. I mean, that's the maximum possible positive number if you had a 16-bit integer, and that's the minimum possible negative number if you had a 16-bit integer. And then the last example, let's say if we have a 32-bit unsigned integer. I think you can see the pattern here that if I mean the positive number is actually the maximum positive number is actually one less than the maximum or the minimum possible negative number in magnitude wise. So if you have an unsigned 32-bit number, so unsigned 32-bit number would go from all zeros. How many zeros in hexadecimal that would have? 8, 1, 2, 3, 4, because 8 into 4 is 32. Each hexadecimal number represents 4 bits, and it would go all the way to all f, all ones, because each f actually represents 1111. Okay, so what are the maximum possible combinations if you have a 32-bit or a 4-byte integer, and that's actually unsigned? It will go from all 0 to what is 2 to the power 32? Let's see. 2 to the power 32 equals a big number, 4294. We have 4294967 So this number, I mean, this is like 4 billion, and that's why we have the 4 gigabytes when we had 32-bit systems, but that's another topic. Okay, so we have maximum number would be from 0 to 42949679295, because we are counting 0 as well. From 0 to this number we have these many combinations. But if we had a 32-bit signed, if we had a 32-bit signed number, 32-bit signed number, 32-bit, so that means it will go from 2 to the power n minus 1 to 2 to the power n minus 1 minus 1, because we are counting from all the way to negative, and we are counting 0, as well as we are going to positive number, and positive number, as we have seen the pattern, is actually one less than the maximum possible negative number in if we are comparing the magnitude only. So 2 to the power n minus 1 would be 31, because we have 32 bits, and it will go from 2 to the power, sorry, I should have the range, and that will be 31 minus 1. So what is 2 to the power 31? And let's 2 to the power 31, obviously it's one less, half of that, so it's a big number, but something like 2 billion. So it will go from minus 214,748,3648 all the way to 214,748,3648. 8 3 6 4 7. Why this thing is significant? Reason is that if you are dealing with some if you are declared some values as integers or unsigned integers or long integers, we should be aware that what is the maximum and the minimum possible value. If we are not aware of the range and we put some large number, we could have a overflow error, or we could have some kind of an overflow error, because I'm going to demonstrate that in a next lecture. But coming to this example which we saw here, I said that I'm going to do that later, or let's just leave it over here. I'm going to explain this in next lecture, why this thing cannot be obviously now it's pretty simple, because 12 cannot be represented in a 4 bits. I need 5 bits for that, because for 4 bits the maximum possible range will go from -8 to +7. I cannot represent 12 in a 4-bit integer, and that's why we have some range limitations, and we need to be aware that whatever variables we are declaring, obviously the minimum size of an integer I think in C++ is 2 bytes if you are talking about some old implementations, and now it's actually 4 bytes, and for long it's probably 8 bytes. But I'm going to see that what the size is declared in the memory for those integers using some kind of a size of function in the next lecture. So this lecture continues to lecture 11, and I'll see you there. In the end, the lecture summary of this lecture is that we did the 2's complement representation or the binary representation for signed numbers, and the benefit of 2's complement is that we can represent negative numbers as well as positive numbers in binary, and if we want to subtract two numbers we actually do addition. Also, we did the ranges of signed and unsigned numbers in this lecture.